I'll start. Good afternoon, everyone. My name is Youssef Abdelkareem, and I'll be presenting to you our paper, Multiplane Neural Radiance Fields for Novel View Synthesis. The co-authors for this work are Dr. Shady, Shehata, and Professor Fakhri, Karray. So the outline of the presentation will go as follows. Let's start by a quick introduction of what novel view synthesis is. Novel view synthesis basically involves it's a computer vision problem that involves rendering completely novel views of a scene using a discrete set of input views given to the algorithm that we have. For example, as we see here, we have 4 input views, and the algorithm should be able to imagine how this scene would look like from any novel scene given to the model, as you can see here in this figure. This particular problem can be used in several applications, for example, in free viewpoint rendering, virtual reality, and it can also be used for performance capture, movie production, telepresence, and many other applications. Let's start by a quick background and related work. So there are several challenges that need to be tackled by the novel view synthesis methods regarding the scenes that they are trying to represent. For example, a main challenge is that models have to have the ability to be able to infer the geometric structure and the texture details of the scenes. They also need to be able to handle or utilize only sparse input views to be efficient to use in practice. They also need to be able to handle complicated scenes with everything related to them in terms of lighting effects, occlusions, and many other challenges in the scenes. They should also be able to handle complicated objects such as humans, for example. So methods utilize different scene representations to achieve or handle those challenges. So these representations can be split into 3 categories. The first representation for the scene are explicit scene representations. The second is implicit and can be split to per scene methods that are only trained on each scene separately, or generalizable methods. They can be trained on several scenes and generalized to new scenes at inference time. There is also the combination of both implicit and explicit representations, and one of them is the pixel level representations. So let's jump into the first type, which is the explicit representations. And one of the most famous representations they call multiplane images. And these have the ability to represent the scene as a set of discretized RGB alpha front parallel planes to model the elements of the scene at different depths. Let's take a look more closely. So as you can see here, we have this input image, and the multiplane image promotes it to a multiplane representation. Each plane represents the elements of the scene that occur at a particular depth. So elements in this particular plane are in the closest depth, and elements at this scene are in the far depth, or the very far depth from the viewer. And this gives us the ability to explicitly model occluded areas. However, the problem is the planes are predicted at discrete depths, which constrains the ability for the model to represent the full 3D space at any continuous depth location, which kind of leads to a 2.5D representation rather than a 3D representation. Another kind of a breakthrough that happened in the field is an implicit representation called Neural Radiance Fields, short for Nerf. And these type of approaches try to have a different approach, where they try to learn the full 3D representation of a scene using a continuous scene function estimated by a deep multi-layer perceptron. So in other words, they basically encapsulate the full 3D structure of the scene within a multi-layer perceptron. So let's take a look at how this works. Let's assume we have this image here of an apple, and that corresponds to this 3D object here in real life. So in order to be able to render 1 pixel in this image, we wash a 3D ray from the camera across the scene passing through this pixel. And throughout this 3D ray, we sample a set of 3D points that can be within the object boundaries or outside. And what happens next is that for each point, we take the 3D location of the point, the viewing direction of the camera, and we pass them to a multi-layer perceptron that outputs the RGB color, the corresponding, or predicts the corresponding RGB color and volume density of the 3D point. So now for this ray, we have a set of predicted colors and volume densities. And here, what volume density means is how much is there an object in this particular point, like if there's no object at all, or is there 100% an object in this particular place. So given these colors and volume densities, they utilize an algorithm or an approach called volumetric rendering to be able to fuse all of these colors based on their volume densities and depth to be able to render the final color of this pixel here. So this method achieves photorealistic output and great output for a lot of scenes. However, the problem is that they require dense views as input, and they are constrained to per scene optimization settings, making them inefficient to be used in practice. So another approach solved this problem, and they are called generalizable Nerf methods. These methods avoid the need to do per scene training and utilize the input image features in order to achieve generalizable properties. So what happens is, given an image, we pass it through a CNN encoder, which produces a feature map that corresponds to this particular image. And now, instead of just for each 3D point, instead of just using the location and the viewing direction, as we said previously, we also augment to it the corresponding feature vector for this particular point by projecting the point on this feature map. So now the multi-layer perceptron is now conditioned on the input image features, which leads to a generalizable property and the ability to infer the structure of completely new scenes on inference or at test time without per scene optimization. The problem with these methods is that they cannot handle complicated scenes really well, and they cannot handle scenes with human subjects, for example. Now comes the last approach, which is a combination of both implicit and explicit representations, which is the MINE approach, short for multiplane neural radiance fields. It is a pixel-level combination of both implicit and explicit representations for novel view synthesis. And what they basically do is that they borrow the volumetric rendering concept and stratified sampling concepts from the Nerf approach and combine it with the multiplane images approach to be able to enhance the performance and to handle occlusions in a much better way. Let's go through what happens quickly. So given a source image, it's passed through an encoder to get a feature representation. And then this feature representation is passed through a decoder at different depth values to predict a multiplane representation. So far, this is very similar to the multiplane image. Nothing is different. However, instead of just each one of these planes to contain only RGB values, they now contain RGB and volume density values, which is very similar to what Nerf is doing. And now what they do is to render the target view, they do homography warping on these planes to transform them to the view of the target camera. And then they carry out volumetric rendering, which is borrowed from Nerf, in order to fuse the colors and the volume densities in different planes together to render the final target image. So technically, they promise and they achieve great results compared to the state-of-the-art methods. However, the drawback is that they are limited to a single view setting, and they are constrained to a narrow viewing direction angle range. So now let's discuss our approach that we're presenting in this paper. So our methodology is split into two parts. We will start by doing an in-depth analysis of the performance of single view MINE from several aspects to study the drawbacks and identify the sources of the problems of the single view MINE and where they could be and why they could be happening. We also propose a completely novel architecture, which is called novel multi-view MINE. And this is an expansion of the existing MINE approach to allow it to accept multi-view input to be able to enhance the performance of it in several ways. Now, let's start with the analysis of single view MINE and the approach that we follow for that. So we started by analyzing the generalization ability of the single view MINE approach. And we did that by doing an inference on a completely novel scenes of the Kitty dataset. And we also carried out inference on completely novel scenes of the LLFF dataset to study how much it has the ability to generalize to those scenes. Regarding performance, we trained the full single view MINE approach on a completely new dataset called the ShapeNet, which is an extremely challenging dataset since it has 360 viewing direction ranges for the objects, which is challenging for the MINE approach. We also carried out some ablation studies to understand which of the concepts that were borrowed from Nerf are actually the most contributing to the best or to the enhanced outcome of the mine approach. So we carried out a comparison between utilizing volumetric rendering and the basic alpha compositing. We also did a comparison between fixed and stratified sampling for the 3D points in the 3D ray. Lastly, we also studied the efficiency of mine versus a very well-known generalizable Nerf method called pixel Nerf. And the intuition here is that mine only models the frustum of the source camera, while pixel Nerf models the full 3D space. So in theory, mine should be more efficient. However, here we study this claim and validate this claim in a more quantitative fashion. Now I'm giving just a quick overview on what's the difference between alpha compositing and volumetric rendering in one of the experiments that we do. So as we said previously, in order to produce the final color of a particular ray, given a set of points and their volume densities and color, there are two methods exist in the literature. So the first method is alpha compositing. And this method involves carrying out an over operation to aggregate the colors based on their alpha value. So nothing fancy is happening here. It's a basic approach and a classical one that just uses the alpha value of each point to aggregate the colors. Volumetric rendering is a much more advanced approach that not only uses the colors, but also utilizes the density and the depth difference between the points and each others. This gives it the ability to better represent occluded areas by taking into account the depth and the volume density at the same time, which leads to an overall better performance for the volumetric rendering approach compared to alpha compositing. Now we discuss the approach of the proposed approach, multi-view mine, and how we were able to expand the single view mine architecture to a multi-view representation. So for that, we did two approaches. The first approach is a post-decoder fusion, where we basically fuse the multi-view information after producing the per-view multi-plane neural radiance fields. So typically what it can be seen in this figure here. So for each image, now we pass them through an encoder to get a feature representation, and then we pass it through a decoder to get a multi-plane representation. However, now we do homography warping to warp them all to the target view or the target camera, and then they are all composed using a composition module that we carry out to compose these multi-view planes together, get the final multi-plane representation. As you can see, it is quite obvious that this method could not be very efficient since we passed or called the decoder several times or n times for n input views, which is not really efficient in practice. For that reason, we propose a pre-decoder fusion module where we fuse the multi-view feature planes before passing through the decoder, which is more efficient than the post-decoder fusion. Technically, what happens now is that all the images are passed through an encoder to get a feature representation. Then they're all passed to a fusion module that we will discuss in a bit in order to produce a final fused representation of these feature maps. And then the decoder is called only once to get the multi-plane representation, followed by homography warping to get the final multi-plane representation at the end. So now let's discuss how do we do the fusion between the different feature maps from different input views. So we propose an attention-based pre-decoder fusion where we learn attention masks that highlight areas of the input views that contain complementing features with respect to the source view. Typically, what happens here is that given a source view image, IS, we pass it to an encoder, and given the other views, we also pass them all to an encoder to get a feature representation. Then for each input image, we concatenate this representation with the source image representation and pass it through an attention masking module. This module is responsible for producing an attention mask given the sigmoid layer at the end. And this attention mask should be able to highlight areas of these images that contain features that complement what can be seen in the source image. So you kind of, in other words, need to focus, gives us the ability to just focus on things in these images that contain features that we're not seeing here. So as it can be seen, what we get this attention mask multiplied by the input feature representation for this image. We do that for all the views, then add them all together to get the final fused representation for all these views together. Now let's discuss the experiments that we did and the results that were achieved. So, We start by showing the results of the inference on the Kitty dataset for the single view mind approach, of course, in the generalization category. So as you can see, these are the outputs and this is the ground truth. The output suffers from severe distortion around the edges of the videos, especially while moving throughout the depth dimension. And you can see also that there's very suboptimal modeling for the occluded areas in different scenes. Now we show the results on the LLFF dataset. So as you can see, these are the scenes that the model saw during training. And these are the scenes that we're asking the model to predict in test time. So the fortress scene is completely new. It's unlike anything the model has seen. However, the flower scene is a bit close to 3 of these scenes here in terms of color and maybe structure. So we expect the model to perform a little bit better on the flowers than the fortress. However, the results will be the one to validate that. So here are the results for it. And as you can see, for the fortress scene, these are the output of the source image rendering. So we're asking the model to just output the source images that were given as input as it is, which is a simple task. And the model is able to recreate the images quite well. So that's an easy task to do. However, when we ask it to render target view images that from completely novel views, the model fails to maintain the geometric structure of the objects in the scene, as can be seen here. For the flowers, it also can be seen that the model was able to retain or to present and render the source images properly with some differences in color, as can be seen here. However, for the target view image, it was able to retain the structure of the flowers. However, it still showed severe distortions around the edges, and which concludes that the model has a difficulty in understanding or imagining how to fill the areas around the edges of the images for the novel views. Now comes the training on the ShapeNet for the performance category. As you can see, for the mine approach, it was unable to even render the object within the image plane boundaries for this particular image. And when the target image became slightly closer to the source image, it has put it within the boundaries of the image plane. However, it's still misplaced in the correct location. For the pixel nerf approach, it is quite accurate in terms of placing the object in the correct location and maintaining the correct geometric structure of the object, which shows the superior performance in pixel nerf on this dataset compared to the mine approach. Regarding the ablations of the nerf, it was seen that the stratified sampling did not actually enhance the results, as can be seen in the first 2 rows here. Fixed disparity or fixed sampling is a little bit better. So, and regarding volumetric rendering, when you compare the first and the last, it can be seen that volumetric rendering produces much better results than auto-compositing, which means that volumetric rendering was actually really beneficial, or it was really effective to be borrowed from the NERF approach and be utilized in this method to achieve better performance. Regarding efficiency, it was seen that the single view mine approach was actually much more efficient than the pixel nerf approach as hypothesized. And in other words, the pixel nerf approach is 38%, sorry, the mine approach is 38% faster on the GPU and 45% faster on the CPU, indicating the validity of the efficiency claim that was made earlier. So now to conclude this part, we have seen that the single view mine approach suffers from edge distortion, suffers from novel view, narrow view and direction ranges, suffers from weak generalizability. We believe that all of these problems are attributed to the single view setting that these models have and the homography warping that needs to be done from the source view to the target view in order to render the novel image. Now comes the multi-view mine results. So we start by comparing the different fusion modules that we proposed. So compared to the single view mine, the post-decoder fusion with basic averaging as a compositing layer enhanced the results compared to single view mine. The pre-decoder fusion is better than the post-decoder fusion slightly on all metrics. The post-decoder fusion with weighted averaging rather than basic averaging is better than the pre-decoder fusion. However, the attention-based pre-decoder fusion exceeds and has superior, noticeably superior performance compared to all the other modules and the single view mine approach, which validates the effectiveness of the proposed module in fusing the multi-view information together to get a better representation of all of the information seen from different views. Here's a qualitative comparison for the output seen As you can see, the mine approach suffers from distortions and large or high blurry artifacts. For the post decoder with the weighted averaging, it solves the blurry artifacts, solves the artifacts around the edges and distortions. And the pre-decoder fusion with attention is actually the best and has the best overall representational ability compared to these two modules. Lastly, we compare this approach to the baseline methods. We achieve comparable performance to some baseline novel view synthesis methods. As can be seen here, our method is better than the S and Nerf on most metrics, and it can also be seen especially better than the SRN on all metrics. And we are also having similar performance to the LLFF and the pixel Nerf approaches. Specifically, we have better performance than the LFF on the LP-IPS and the SSI metric. We have better performance in pixel Nerf on the PSNR metric and on the SSI metric specifically for the pixel Nerf approach, which indicates the strength of our approach and compared to some strong and very well-known state-of-the-art baseline novel view synthesis methods. So to conclude, we demonstrated the single view mine approach has weak generalization and a small viewing direction range due to single view input or maybe homography warping. We also concluded that volumetric rendering plays a more important role than stratified sampling in achieving better results. We've also seen that the single view mine approach is more efficient than the pixel Nerf approach. We also proposed a multi-view mine architecture that utilizes a novel attention-based module to effectively fuse multi-view features and enhance the synthesis quality for mine. For the future work, it is good to look into avoiding utilization of homography warping for target view rendering and to look into ways to render completely novel views from the predicted multi-view or multi-plane representation directly. Here are the references. And thank you for your time. I'll be happy to hear or answer any of your questions.